So till now we have talked everything about the introduction to this course. So now we will start with module 1. This is basically like for theory of computation part. This module will cover all the basic terms and definitions and everything. So the whole goal of theory of computation is to mathematically define what computing is. Okay. I mean, theory of computation is not just for as like basics for compiler design. It is actually a more broader topic which evolved way before compilers were even born. So, theory of computation mainly to define what computability means actually. So the idea was to formalize all mathematics into representation using a finite set of symbols. So they wanted to like group the whole mathematics into formal manipulation of finite set of symbols. So this was the initial the goal of understanding what it means to be computable. I mean, this all seems very strange now, but please stay. So eventually there was some theorem called Gödel's incompleteness theorem that stated basically this is not possible. Right, so okay, we will come to this part later. This is very high level stuff that we do not require. You can read that in some book I will mention later. Okay, you can actually read this in the Dexter C. Cozen Automata and Computability. In this lecture 1, it is just 3 pages. You can find the PDF online and read if you want. So we will proceed with our course. So theory of computation in our course is basically our goal is to like mathematically and formally define what a language is first before we can create programming languages and write compilers, right? So before we need to do all those, we need to first formally define what a language is. So we first basically define some basic terms and definitions. Before we do that, we will come to the definition of language in a few minutes, but first we need to look at some other definitions like alphabet. So alphabet is a finite set of characters. We denote it by sigma. Like for example, a finite set, okay, this is the important part. It has to be a set of finite length. So an example is sigma 1 equal to set of 0 and 1. These are just characters here, not numbers. Like in C, you have seen char, it's a 1 byte character. So these are just characters here, just symbols. They don't have any meaning yet. So sigma 1 is a set of 0 and 1 characters, and sigma 2 is another example of an alphabet set. This is a set and it is a finite. We have 3 symbols or characters. Both are basically same. Okay. And another definition here is string. String is basically, you have seen in C or Java or Python, it is just a string of characters. But when we say a string, it has to be finite and it has to be generated from a given alphabet set, not just any random. So if we take an alphabet set sigma to be set of elements a comma b, we can generate different kind of strings, right? So this is an example of string a b b a generated only using a and b, and this is another example of a string b b b b b b 6 b's, all generated using this alphabet set. So this is just a string definition. And then we define another thing called an empty string. We denote it by small epsilon. Do not confuse with the belongs to symbol. It is very similar. I think we use same, but this is more, belongs to symbol is more like this. Epsilon is somewhat like E, I think. I mean, they are very similar, but we still use this symbol. Okay. So an empty string epsilon, it is basically a string of length 0. Okay. So if you look at these strings, these have length 4, this string have length 6. An empty string we define, it is basically of length 0. It has nothing. We just denote it using epsilon. That's it. It doesn't have anything inside it. Why do we have to define an empty string? We will now see. So now let's look at this. It is an operation, concatenation operation on strings. So concatenation is basically like if you have strings x comma y, concatenating means joining them end to end. So x and y. If x is basically ab and y is just bb, so concatenating meaning we just join them a b b b. That's it. That's what we have written here. Concatenation of strings. X and y are strings made from sigma. Then concatenating x comma y is basically joining them, xy. So examples we have here, if x is ab and y is ba, then concatenation of x and y is abba. Similarly, another example, concatenating A and B, we get AB. And now if we concatenate string BA with epsilon, epsilon is empty string we have seen here. Okay, so concatenating BA with empty string, you just get BA, right? Or concatenating epsilon with BA, you will still get BA. So epsilon is an empty string here. We will use this kind of concatenation and some other things in future. So an empty string has to be defined now. That's why we do that. Okay. Now let's look at this another definition, universal set U or sigma star. Okay, so we are here going fast in this because this is a video. You can pause and watch anytime. This is, you can watch it at your own speed. Okay, that's why I'm going very fast here. Okay, so if you want to please pause at the definitions and write down those definitions in your notebook. These definitions are very important. Okay, I will also share this as a PDF version that you can read. So the video will be fast, so please pause and watch and understand everything. Okay, now let's look at this new definition, sigma star or universal set U given sigma. So universal set is basically sigma star. Sigma we have seen before. Sigma is alphabet, finite set of characters. So sigma star is basically, it is the set of all the possible strings we can generate from a given alphabet set sigma, including the empty string. Okay, so now let's look at an example. If we take sigma as just set of a single element, single character A, what kind of strings can we generate using this single character? And by default, every sigma star must contain epsilon. Sigma star we can also say like set of all possible lengths of strings, or like just set of all possible strings of all finite lengths, right? This is another way of looking at sigma star. So now if we want to generate sigma star for this A, now we can do this. We can just look at first what are all the possible length 0 strings we can generate. Only epsilon, empty string. Now using this character only, what are the strings of length 1 we can generate? Only of, and all the possible strings of length 2, what can we generate? A, and so on. So this is all the possible strings you can generate using only this given alphabet, right? So now let's look at the next example. Now if we have 2 elements in our alphabet set, what all possible strings can we generate? So let's first generate all the possible strings of length 0, which is only epsilon empty string. Now what are all the set of possible strings of length 1 we can generate? Basically A and B. Now length 1, length 0. So what all possible length 2 strings can we generate now? Using just A and B. We can generate AA, we can generate AB, BA and BB. These are all of length 2 that we can generate from these two characters. And we can, what are all possible length 3 strings we can generate? We can generate like AAA, AAB, ABA, ABB and BAA, BAB, BBA, BBB. These are all the strings of length 3 we can generate. So length 4, length 5, so on, we can go to infinite, right? So these are all the possible set of strings that we can generate for this given alphabet set. Similarly, another example is 0 and 1. If you like, this is the same example as this. Instead of A and B, we have 0 and 1. So what all strings using 0 and 1 we can generate? Basically an empty string, a string 0, string 1, and of length 2 what can we generate? 0 0 0 1 1 0 1 1, and length 3 basically this, with replace A with 0, B with 1. So this is basically the definition of sigma star. Set of all strings possible using sigma. That's it basically. It is, we call it sigma star or U, the universal set. Okay. Okay, so now that we have seen sigma and sigma star and what is a string and what is an empty string here, epsilon. Another point. Sigma star is always an infinite set because the length of strings that we can generate basically is always infinite. So we can always have infinite strings in this. But every string has to be a finite length because string by definition is always finite. And we call this infinite, actually we call this a countable infinite. There is actually countable and uncountable infinite. This sigma star is actually a countable infinite. We will not discuss much about this, just countable and uncountable. This concept, it will be used in like proving the above Gödel's incompleteness theorem. We will just discuss. I will give an optional video that you can watch or not watch, but I will just give the result. The proof is optional, you can watch it or not, your choice. I will put it at the end of this today's week. Okay, so now that we have seen sigma string, empty string. This is actually epsilon, not this. This looks more like belongs to. So we will use this from now on. Okay. And we have seen sigma star. So now we will look at what is a language. So a language is any subset of sigma star. We can call a language any subset, and this does not look anything like real language or anything, but please stay here. So for example, if we take sigma as 0, 1, we saw what sigma star can be. Epsilon 0, 1, 0, 1, 1, 0. All the possible strings you can generate with these two. So any subset of this is a language basically. So this is definitely a subset of this. So we can call this a language. And set of all strings that only contain odd number of zeros. It has 1, 3, 5. These are all part of this. So this is another subset. We can call this a language. This is a finite subset language. This is an infinite subset language. So a language is basically any subset of sigma star. We can just call it a language. We will see how this definition of a language will be used later. So this is the basic definition of language. And again, L is just a set, a subset of sigma star, right? Constructed on a given sigma. Before we can give a language, we must specify the sigma, because we construct a language on sigma star, right? So every language must give a sigma beforehand. So now that we have seen the definition of a language, let's see how we define a computational problem. Okay. So L is basically a subset of sigma star. Given a sigma, we are given a language and a string, both made from sigma star. X is a string that belongs to this set, and L is a set that is a subset of this set. So computational problem is basically given a language and a string made from sigma. Decide whether X belongs to L or not. L is a set, X is a string, whether or not this string belongs to this language set. That is basically a computational problem. To solve this, so this looks very simple because L is just a set, X is a string, we can just look up, but it is not easy. It is easy if L is a finite set, right? We have seen an example of a finite subset. Yeah, this is a finite, but this is infinite, right? If L is finite, we can just look at every element in L and see if it is X or not. Easy to solve this computational problem. But if L is infinite, we cannot just give all the elements, right? We can give some elements and just say in this series this is an infinite subset. Yeah, if L is finite, is you can look up the whole set and look for this x. But if L is infinite, that's where we run into problems, right? So let's look at this example. For given sigma as 0 and 1, assume this is our language, empty string 0, 1, 1, 1, 1, 0. This actually follows a pattern. This is the basically binary representations of all numbers divisible by 3. So this particular language example, this is just a set of all the numbers that are divisible by 3, here given in binary representation form. So this is an infinite set since there are infinite number of numbers that are divisible by 3. So for infinite language we cannot specify all the elements, but what we can do is give a description of that language. In this case we can say all the numbers divisible by 3, right? So for a language what we can do is we can just give a finite description, right? So a finite description must be given for any computable language. Computable meaning we can identify the computational problem and we can build machines to solve the computational problem. We will see what a machine is. Okay. So every language must have a finite description. Even though the language is a finite set or infinite subset of sigma star, it must have a finite description. That's how we can formally and mathematically describe a language. Finite description meaning like, let me come there in a few minutes. So a language can be an infinite set, but describing should be possible finitely. So how can we finitely describe the set of all possible strings that are divisible by 3? What we can do is basically x belongs to, we can just write this set in roster form or whatever. Like we can write x equal to set of x such that x belongs to sigma star and x is divisible by 3, or we can write this x mod 3. So if we think of these as like finite symbols, we can just construct a finite set of all these symbols and all the basic mathematical symbols, and in this mod, this as a function, we can give a finite description, call this another language and recursively like. So this is an accepted finite mathematical description. Okay. So when I say a finite description, it must be like, it must also be constructed using another finite set of symbols. In this case, let's say gamma It looks more like tau. Okay, this, right? Tau. Let's call it another finite set of symbols we use to describe languages. So when I say language must be described finitely, at the end it must be also be able to be written in a finite string of that is made of another finite alphabet set. That's what I meant basically. Okay. Now that we have seen definition of language and a computational problem, let's go further. Look what is a machine. So a machine is basically, it represents a single language L, and this machine is built using the finite description of this language L. It can only represent this language currently. So it will take input as any string, and now it has language and a string. It solves the computational problem and gives output as yes or no, which is basically does x belongs to L or not. Solving the computational problem for the language L, it is called a machine basically, right? So for every language that we can finally describe, every language that we can give a finite description for, there exists a machine capable of solving the computational problem for that language. Okay. Okay, I need to make an addition here. Okay. For every language that we can finitely describe, and that language must be computable. We will see later in Turing machines that there exist some languages with finite description that are not computable. So for those languages we cannot build any machine even though they are finitely describable. The main thing is any computable language. I should have written computable, right? I will write here. Every computable language we will see what computable means in Turing machines part. Okay, no worries. A machine exists. Machine that can solve the computational problem for that language, right? Yeah, we will see what computable means later, but for now just take that if the language is computable, it will have a machine, and this is also should be modified. Okay, so now that we have seen what languages are basically, we can now come to this. So the main kind of languages we will deal with in this course are regular languages, context free grammars, and this recursively enumerable grammars or recursive grammars. So, yeah, like I said before, every language that is computable will have a machine existing for that. So, for these kind of languages, for these different categories of languages, we have different categories of machines, right? So, for regular languages, we can build these kind of machines. So, a machine is basically this, right? This is y, and a machine model is basically like a type of machine. How can we say, like, we have different kinds of car engines, right? Like we have different kind of cylinders. For, like, we have 4-cylinder engines, 6 cylinders engines. In 6 we have inline V-shaped. So if we call these different kind of machines, we can call these are all part of a internal combustion engines. So if these are different machines, this we call a model, right? Model is nothing more than that. It is just like categorizing these kind of machines. So DFA, NFA, epsilon NFA, these are a category of machines. These are different kinds of machines. Just the language specific part will change, right? So these are different kind of machines. For regular languages, we use these kind of machines, and for context-free grammars we use these kind of machines, and for these we will use Turing machines. And we will also see that from top to bottom the power of machines increases, meaning basically the bottommost machines can represent more kind of languages, right? So again, as these can represent more languages, the regular languages, context free and recursively enumerable. Let's just look at this. So Chomsky hierarchy of languages. Regular languages are this one. This is completely a subset of context free grammars. So regular languages, this is completely a subset of context free grammars, and this is completely a subset of third one, and these are the whole set of languages, this whole. And here we will have some other languages that do not have any finite description, that are not computable. For those we cannot build machines. We cannot talk about this because they are just not representable, so they are part of this, right? So let me just show a picture online. Yeah, this is basically regular languages, completely subset of context free grammars, which are completely a subset of context sensitive. We will not discuss unrestricted or type 0. In this, there is, how can I write here? Okay, so the main goal is to say that regular, these are all like a hierarchy of languages. Completely one is subset of others. That's what we are trying to tell here. Okay, so now that we have seen this, every class of language has their own corresponding model of machines. So next week we will start with regular languages and these models. Okay, and yeah, so before that we will discuss some other things, some basic operations on languages, since languages are basically some sets, subsets. We will just look at some operations that will be helpful for us, and next week we will dive into regular languages. Okay, so another thing I want to add here is, so we talked about this. Yeah, so I mentioned this will represent regular languages. This will represent context-free grammars. This will represent recursive languages. So here when I said top to bottom the power increases, I meant we have seen regular languages is completely a subset of context-free grammars. So these has to represent more languages. These machines, top to bottom, they will have more power. Let me tell you why. Because these machines are basically finite state machines. Finite state machines. So they are basically like a set of states. So all these machines have some things in common. I will discuss now. So every machine has a finite set of states. All the machines have some finite amount of states, and there will be one start state or multiple start states, and there will be some final states, right? So every machine has basically this finite amount of states, and there is one tape, not tape but your X. Basically all the characters are written in order, all the characters in string X are written in order. So in all the states they have some rules. So reading one character, it will go from one state to another state. Reading another character, according to that state's rules, it has to go to another state upon reading this character. Likewise, it will transition from state to state according to the transition rules, which are guided by these characters. So it will start at any of the start state and move along states. So I will discuss later. Okay, so what I want to tell you is, for finite state machines, for regular languages, we only have states, finite states and finite transition rules. For these machines, we will additionally have another supporting stack. A stack is basically some data structure, right? So we will have a stack along with these finite state machines, and that will give us more power to store some things and give more power to represent more stuff. And for Turing machines, we will have more than a stack. We will have some another operation on stack which will let us to move forward or backward also. So the more power these machines, as we can see, like from top to bottom we are increasing more functionalities for these machines. We are allowing more functionalities, so that's why these machines are more powerful from top to bottom. And individually we will see, okay, what these all actually, how this all works. Okay, I should not have said this part, just forget. Like, don't worry about it too much. So now we will come to this. So concatenation of strings. Concatenation of strings we have seen before. Given two strings x comma y, just x y, writing end to end. That is what concatenation is basically. We have seen here. Yeah. X and y are strings made from sigma. Just add them. AB and BA will give this. Concatenating A and B will give this. Concatenating BA with an empty string gives you just BA. So that is what basically concatenation means. So now let's look at what concatenation of languages is. So given an alphabet sigma and two languages L1 and L2 are languages over sigma star. So L1 concatenated with L2 or just L1 L2, it is basically xy set of x comma y, x set of x concatenated with y such that x is a part of L1 and y is a string from L2, right? For every string x in L1 and every string y in L2, concatenate all those strings. L1 L2 is a set of those. Okay, so this is like very similar to Cartesian product. Cartesian product, we just write them as tuples or pairs, if you will. Cartesian product of sets is basically for every element A in A and B in B, A comma B, that is a tuple. But in this case we just concatenate those strings instead of writing as tuple and form a set. Okay. So in Cartesian product example we can see if A is a set of 0 and 1 and B is a set of A and B, Cartesian product is basically multiply this to every element of A with every element of B. So 0 A, 0 and B, and 1 and A, and 1 and B. So that is basically Cartesian product. So let's look at an example of concatenation of languages, right? So you can see here, just multiply every element of this with every element of L2, right? So concatenate AB with epsilon, you will just we'll just get AB and AB with A, ABA, and you'll get AB with B, and with this also multiply everything, BA, BAA, and BAB. And another example is this. What will we get here? ABB, this and this, and AB with epsilon will get AB, and AB with A, ABA, and ABB with B, ABBB, and ABB with epsilon, ABB with A. But since this is a set, we will always remove duplicates. So in this case, these are duplicates, right? So we will remove those. Again, this is also for the same reason. Cartesian product never exactly have m times n elements, right? There will be duplicates. So m times n is basically the maximum possible elements, right? So this is basically concatenation of languages. We write as L1, L2. Okay. So now let's look at other things. So given L, we can write L square as L concatenated with L, or L dot L, L cube as L dot L dot L, or L square dot L, or like L dot L square, or L power 0 times L cube. And this is, we define every language L power 0, we just define as set of one string, which is empty string, epsilon. Okay. So this is by definition we are giving every language power 0 is a set of single element, which is the empty string. Why we will need that? Because we will see shortly. So okay, just let me say, because if we write L is basically L power 0 times L power 1, we can write, right? So L power 1 is basically set of L, it's all elements in L. But here, if we give an empty set L power 0, then this will become an empty set, right? So that's why if we put the empty string here, it will concatenate with all these strings, right? So empty string concatenated with all these strings, which will do what? Nothing basically. It will just give out all these strings again. Like if L is like AB, BB, and BA. So what is L power 0 times L power 1? Which is empty string and AB, BB, and BA. Now if we look, empty string concatenated with AB, AB, empty string concatenated with BB, BB, and BA. So this is why, to keep our set notation all this L power 1, all L power 2, to keep those definitions, to preserve the meaning, we need to define L power 0 as this. Okay, that's the idea. So yeah, L power 0 we defined as set of one string which is an empty string, and L square we define as L concatenated with L. Like similarly, L power k we define as this L concatenated k times over. And now we will look at this operator L star. We call this asterisk of L, which is basically a union of for all k greater than 0 equal to L power k. So this is another definition. This is basically L power 0 union L power 1 union L power 2 goes on up to infinite. Okay, another thing we can add here is there is also something called L plus, which is basically union of starts with k greater than 1. This starts with 0, this starts with 1. L plus L power k. So it is basically like L star is that's it. This is like whole numbers, 0 included. This is like natural numbers, only non-zero, non-negative, greater than or equal to 1. Okay. So now let's look at some other thing, some small thing basically. Okay. So can we agree that from sigma we make sigma star, but we can say that sigma is a subset of sigma star, right? Sigma is basically finite set, which is also all characters are basically strings of length 1. And sigma star contains strings of all kinds of lengths, 1 included. So sigma is actually a subset of sigma star. So we can call sigma also as a language, right? So now let's look at a language which is basically sigma. So then what will be sigma power 0? As defined before, any language power 0 is just an empty string, set of one string which is empty string, right? And what is sigma power 1? In this case, I assume sigma is an example a comma b. So sigma power 1 is basically a comma b. What is sigma square? A comma b times a comma b, which will generate 4 strings a b, ba, and bb. And sigma power k is something. So what can we say about this? We can say this is set of all strings of length 2, right? Set of all length equal to 2 strings. This is a set of all length 1 strings. This is set of all length equal to 0 strings. So similarly, if we go that way, sigma power k is set of all strings of length k. So sigma star is basically sigma power 0 union sigma power 1 union. Set of strings of all different lengths. Possible lengths. So if we take L as sigma, the language as sigma itself, sigma power anything would be set of all strings of that length, basically. This is just a special case of sigma. And sigma star, we have seen the definition sigma star, and we have seen the definition of L star. What I am trying to say here is the notations are very perfect here, right? This is the definition of L star, which is perfectly matching with sigma star if we take L as sigma here, right? So that's a nice observation. Okay, so let me just conclude what we have seen this week. Okay, we have seen in theory of computation sigma set of finite set of strings, finite set of characters, and we have seen there is an empty string epsilon, and we have seen sigma star, which is set of all possible. This. And we have seen the definition of language, which is basically any subset of sigma star. We have seen computational problem given nx and L, give x belongs to L or not, and a machine that solves a computational problem for a given language's description. We can construct machines if we can give a formal description for any computable problem. So this is the summary of this week basically. So next week we will start just building machines for regular languages. Okay, and I will include the optional video later now. That is your choice. So what the result of it is basically there are infinite, we know that there are infinite elements in sigma star. So that means infinite subsets of sigma star. So that means infinite languages exist, but let's okay. So there exist infinite languages, but not all languages have finite descriptions. We will see later. This is the optional video that I will give proof for this, but just keep in mind not all languages have finite descriptions. So that means not all languages have machines to solve computational problems. For that, and again, when I said computational problem, I only said that x and L give x belongs to L or not. You might ask, how can this be a problem, right? Like we can see like different kinds of problem. This does not look anything like a problem. Like how can this be enough to represent all problems, right? So this is what we call a decision problem. We output yes or no. So we call this decision problem, right? But we have also functional problems. Which are basically like f takes some input x and gives y. So these are kind of functional problems. But we can say that every functional problem can be built using a lot of decision problems, and every functional problem can be solved eventually using just only decision problems. Okay, like I will give an example. So if we want to like find out f of 10, which is basically root 10, let's decide a decision problem. What we will use is basically some x square greater than 10 or not. So what we can do for 10, we start with 1. Start with x equal to 1. 1 square greater than 10 or not. It will output no. Okay, so for 2 it will still give no. For 3 it will give still no. For 4 it will give yes. So from the point it will switch from no to yes. You will take that as the answer. So integer square root is basically 3 here. So this is a very trivial example. We have many other examples like finding out if a number is prime or not. No, like okay, we have some other examples I will include in the notes later. You can check out yourself. Okay, so now here I will stop, and the conclusion of this whole week is basically this. We have seen definition of all these. and I will just say that this is the only week where we have this much theory intensive part. From the rest of the for the future of this course remaining part, you will not have this much theoretical, mostly like just solving problems, okay, like building machines. And in compilers we will look at, it is also like problem based, lot of problems, lot of grammars. So just this week the introduction to theory of computation is just theoretical. Okay, now I will stop here, and as I mentioned, I will just give a result, a proof for this in a optional video after this. Okay, not all languages have finite descriptions, so not all languages can be represented finitely, and some languages, those such languages, we cannot build any machines to solve computational problems. That is an optional proof I will give in the next video.